Hello guys, welcome back. This is problem set 11 of the lecture series Signals and Systems. So in this video, we'll be discussing some problems on sampling and DFT. So let's get started. Going to the first question. A continuous time signal x of t is obtained at the output of an ideal low pass filter with cutoff frequency omega c equal to 1000 pi. So this will be in our actual sense, whatever we discuss, this will be our omega m. If impulse train sampling is performed on x of t, which of the following sampling periods would guarantee that x of t can be recovered from its sampled version using an appropriate LPF? So what it is asking is, it's asking to find the sampling frequency, or here the sampling in terms of the sampling period. So 2 pi by t. And from the sampling theorem, we know that our sampling frequency should be at least 2 times the bandwidth of the signal, right? So here omega m is nothing but 1000 pi. So my omega c should be greater than 2 into 1000 pi, which is 2000 pi. So what about my t? So 2 pi by t is greater than 2000 pi. So t should be less than 2 pi by 2000 pi, which means it is 1 by 1000 or 10 power 3 minus 3. So now let us check the options, which of them is less than 10 power minus 3, right? So 0.5 into 10 power minus 3 is definitely less than, right? So which of the following would guarantee? So this would guarantee. So I'll put yes. What about 2 into 10 power minus 3? It is greater than 10 power minus 3. So no here. And here 10 power minus 4 is also less than 10 power minus 3. So yes. So this is how you use the sampling theorem to find the solutions. So let us move on to the second question. In the system shown below, x1 of t and x2 of t are multiplied together and the product w of t is sampled by a periodic impulse train. So here we can see x1 of t and x2 of t are multiplied and that gives us w of t, and that is sampled with the p of t, which is the impulse train, to give me wp of t. x1 of t is band limited to omega 1 and x2 of t is band limited to omega 2. Okay, so what they are saying is my x1 of j omega is something, so it is equal to 0 for omega greater than mod omega 1. Sorry, mod omega greater than, well, we can also say greater than or equal to omega 1. And my x2 of j omega is equal to 0 for mod omega greater than or equal to omega 2. Determine the maximum sampling interval t such that w of t is recoverable from wp of t through the use of an ideal LPF. So it is similar to the previous question. Same concept of sampling theorem you have to apply. But here the w of t is nothing but x1 of t into x2 of t. So if we take a Fourier transform, I'll get w of j omega as x1 of j omega convolved with x2 of j omega. Of course, you will have 1 by 2 pi factor. But we are interested in the domain frequency range of this, where this signal is non-zero, right? So when we convolve two signals, what will be then? So your x1 of j omega is something like this, minus omega 1 to omega 1, and your x2 of j omega is something like this, minus omega 2 to omega 2. So if you convolve these both, you will get a signal which is there from minus omega 1 plus omega 2 to omega 1 plus omega 2. So this we know from our previous classes, right? So my w of t or w of j omega, or okay, I'll write w of j omega is equal to 0 for mod omega greater than or equal to omega 1 plus omega 2. So this is my important condition we got. So it's another words to say this is my w of t is band limited to omega 1 plus omega 2. So to recover omega p of t, what should be the sampling frequency? So omega c sampling frequency, or we used to call it omega s, right? So omega s is nothing but, it should be 2 times omega m, and here omega m is omega 1 plus omega 2, right? And what they're asking for the maximum sampling interval. So my t should be greater than, so here this should be greater than or equal to, since we can consider greater than, equal to also we can consider, because at omega 1 and omega 1 plus omega 2 itself, it is going to 0. So anyway, my t should be less than omega s by 2 pi, or it is 2 pi by omega s. So which is nothing but pi by omega 1 plus omega 2. So my maximum sampling frequency is, sampling time period is pi by omega 1 plus omega 2. So this is what they have asked. Determine the maximum sampling interval t such that W of t is recoverable from Wp of t through the use of an ideal LPF. So the answer is pi by omega 1 plus omega 2. Okay, moving on to the next question. The first 8 points of a 8-point DFT of a real valued sequence. So they have given that the sequence is real valued. So my x of n is real valued. And 1, 2, I think this is 5 points. First 5 points of x of k they have given. So it is 0.25, 0.125 minus j 0.3018, 0, 0.125 minus j 0.0518, 0. So we have 1, 2, 3, 4, 5. So it is like, in terms of the indexes, it will be 0, 1, 2, 3, 4, and we need 5, 6, 7 to make it a 8-point DFT. So I will call it A, B, and C. Okay, so this will be my x of k. So now I need to find A, B, and C, and the only information given is my x of n itself is real valued. So let us try to see what information we can get out of it. So let me write my DFT formula. So I have x of k is equal to n equal to 0 to n minus 1. Here n is 8, so it will be up to 7. I will have x of n e power minus j 2 pi by 8 kn, right? So now I will take x conjugate of k. Then what I will have, n equal to 0 to 7, x conjugate of n e power j 2 pi by 8 kn. But I know my x of n is real valued, so my x conjugate of n is equal to x of n. So if I substitute, what will I have? N equal to 0 to 7, x of n e power j 2 pi by 8 kn. Now I need to write this in the form of x of k itself. So I will replace k with minus k so that I get a minus sign here. So x conjugate of minus k is equal to summation n equal to 0 to 7 x of n e power j minus j 2 pi by 8 kn. But this is nothing but my x of k itself, right? In other words, I can get my x of k is nothing but x conjugate of minus k. But this minus k is, again, we are doing a circular reversal, right? So then I will get x conjugate of n minus k, and here n is 8. So I will get x conjugate of 8 minus k. So what will those indices be? If my k is 0, it will be 8. So which is nothing but 0 itself. If k is 1, it will be 7, 6, 5, 4, 3, 2, 1. So my a will be nothing but x conjugate of 3, right? And my b will be x conjugate of, okay, I'll write this out. So this is nothing but, my 3 is here. So 0.125 plus j 0.0518. My b is nothing but x conjugate of 4 right? No, b is here x conjugate of 2 because it is 6, x of 6. So I'll write that also to give you a clarity. So a is nothing but x of 5. See this one, which is nothing but x conjugate of 8 minus 5, which is 3. Similarly, b is x of 6, which will give me x conjugate of 8 minus 6, which is 2. And 2 is nothing but 0. So this will be 0. Similarly, my c is x of 7, which is x conjugate of 1. So which is 0.125 plus j 0.3018. So this is how to find the remaining sequence. Okay. So you need to see what additional information they have given. If you miss this real valued sequence, then you may not be able to find it. Okay, let us move on to the next question. Consider the sequences x1 of n equal to 0, 1, 2, 3, 4 and x2 of n is equal to 0, 1, 0, 0, 0 and their 5-point DFT. Determine a sequence y of n so that y of k is equal to x1 of k into x2 of k. So it is multiplication in the DFT domain. So in my IDFT domain, it will be circular convolution. So x1 of n point circular convolution. Here n is nothing but 5. x2 of n. So this is nothing but summation. I'll take k equal to 0 to 4. x1 of n or x1 of k, x2 of n minus k. Again, this is gonna be circular shift. Okay. So how do I compute this? So first I'll take x1 of k. So this is nothing but 0, 1, 2, 3, 4. My x2 of minus k I'll take. x2 of minus k will be x2 of 0 will be same, right? And only these will be shifted. So 0, 0, 0, 1. So now I just multiply and keep shifting one by one and then I can find my y of n. So my y of 0 is nothing but this into this, right? Which is nothing but when I multiply this, only 4 will be left. So this will be 4. My y of 1 will be this into 1 minus k, which is nothing but a right shift by 1. So 1 will come here, all these 0 will be pushed. So this is nothing but 0. Similarly, my y of 2. This will be 2 minus k. Again, I have to right shift by 2. So my 1 will come here and everything will be 0. So this is equal to 1. And y of 3. Again, you don't have to write this every time. Just if you write it once, it's enough. You just keep moving this 1. And then you will get 4, 0, 1, 2, 3. So just for your sake to understand better, I am writing it out. Otherwise, if you are doing in a GATE exam, you have to solve it faster, right? So then you need to write all these steps. So here I have to shift by 3. So my 1 will come here, 0. So this will be 2. Similarly for y of 4. This will be, my 1 will actually come here. So this will be 3. So my y of n is nothing but 4, 0, 1, 2, 3. Okay, this is how you perform a circular convolution. Okay, now let us see some GATE questions. So the first question, for a vector x equal to x of 0, x of 1 up to x of 7, the 8-point DFT is denoted by capital X bar, which is given as DFT of the small x, and which is given as capital X of 0 up to x of 7. And the formula also they have given, x of k is equal to summation n equal to 0 to 7, x of n exponential of minus j 2 pi by 8 nk. And here j is equal to root of minus 1. if x bar is equal to 1 0 0 2 0 0 0 and y bar is equal to DFT of x. So y bar is twice you're taking DFT on x. Then the value of y of 0 is, so if you observed in our notes, if you observe the duality which we discussed at last, in this we said if x of n gives DFT as x of k, but if I take this x of k itself as a sequence and then try to take its DFT, then I was getting nx of minus k. So my y of n will be equal to nx of minus k, right? Y of n or y of k you can also write, because it is a DFT of DFT. Okay, and they are asking value of y of 0. So my y of 0 is nothing but n into x of 0. Here n is nothing but 8 point DFT. So nx of 0. X of 0 is 1. So 8 into 1 is 8. So your answer is 8. But let's say you don't remember this formula, you forgot in the exam. So then what you have to do? Then you have to go back to your basics. So you already have the DFT of x, right? You have x of k. So you have x having a DFT of x. So your y bar is nothing but DFT of this x, right? And this is nothing but, if you use this formula, n equal to 0 to 7, we will have x of n exponential of minus j 2 pi by 8 nk. So this is nothing but your y of k. And x of n itself is what, using this DFT? Your x of n itself is nothing but summation some m equal to 0 to 7 x of m e power minus j 2 pi by 8 nk. So that you substitute here. You will get y of k as summation n equal to 0 to 7 summation m equal to 0 to 7 x of m e power minus j 2 pi by 8 mk, this is m, into exponential of minus j 2 pi by 8 nk. Now you reverse the summation. So you take m outside, x of m, then you take n inside. So n equal to 0 to 7 exponential of minus j. Oh sorry, this is involving n and m, right? So this will be n into m. So similarly here it will be n into m. So now if you write, you will get exponential of e power j 2 pi by 8. N is common here. So n into m plus k. So now we have to find this summation. So again this we know, summation n equal to 0 to 7 a power n. This is nothing but 1 minus a power 7 by 1 minus a, or 1 minus a power 8, right? Because this, it has 8 terms. This is when a is not equal to 1, and if my a is equal to 1, I'll just add 1 8 times, which will be equal to 8. So if I then notice this, my a is nothing but e power minus j 2 pi by 8 into n is the summation term, so m plus k. So this a is equal to 1 when my m plus k is a multiple of 8, right? 8 multiple of 8. Okay, or in other words, when my m plus k modulus 8 is equal to 0. In all other cases, what is happening to this? My a power 8 will be e power minus j 2 pi into m plus k, right? This is going to be equal to 1. So in all other cases, this will go to 0. So 1 minus 1 will go to 0. Only in this case, it will become 8. So my y of k is nothing but summation m equal to 0 to 7 x of m, and I'll put a delta function, and that will have value 8. 8 into delta of m plus k is mod 8 is equal to 0. So when is this possible? When my x of m is replaced with minus k, right? M is equal to minus k, we can take mod 8. So this is nothing but 8 into x of minus k mod 8. And for y of 0, this is nothing but 8 into x of 0, which is nothing but 8 itself. So that is what we derived. This is using duality, we saw that. And using the entire formula and derivation also, we are getting the same thing. Okay. So moving on to the next question. Consider two 16-point sequences, x of n and h of n. Let the linear convolution of x of n and h of n be denoted by y of n, while z of n denote the 16-point inverse IDFT of the product of the 16-point DFTs of x of n and h of n. But what does this say? It is not, this z of n is nothing but circular convolution of x of n and h of n. The value of k for which z of k is equal to y of k is or. So they're asking at which value of k will my linear convolution be equal to circular convolution. So first I have my y of n is nothing but my linear convolution of x of n with h of n. And then I have z of n, which is nothing but my circular convolution of 16 point circular convolution of x of n and h of n. So how will I do my linear convolution? I'll take x of some k, so which I'll have it like this. So x of 0, x of 1 up to x of 15. So this is my x of k, and then I'll take h of n minus k, and I'll keep shifting. So I'll consider n as 0. Then what will I have? I'll start from, this is the origin. Let me line it up. I'll have like this up to h of 15. Right? Now as I put n here, this will shift n times. Okay? So I'll check the same in the circular case. So I have x of 0, x of 1 to h of x of 15. Similarly for h of minus k, what I have? I'll have h of 0 and all other things will be shifted. So h of 15 will be reversed, to h of 1. So now what will be my y of 0? It will be this multiplied by this and a summation of them. Even here it will be this multiplied by this and summation of them. Clearly you can see only when these both are equal will my y of k will be equal to x of k, right? So for y of k equal to z of k, and this I'll call it 1 and 2. Both 1 and 2 should coincide, right? So for 0 case, you can see only this is the term x of 0 to h of 0 in the linear convolution. But in the circular convolution case, you have x of 0 and h of 0 plus these terms are also coming. So for 0, it is not the case. What about 1? You shift 1 here. You will get h of 0 into x of 1 and x of 0 into h of 1. But here again you will get the entire term. So 1 also nothing. So we should then see where the entire thing of this will coincide with the entire thing of this. So let us take for n equal to 15. So in this case what will happen? I will have x of 0, x of 1 up to x of 15. And h of 0 would have come here. And my h of 15 would have come here. Right? This will be h of 14 and so on. Similarly, in this side what will happen? I'll have my x of 0, x of 1 up to x of 15. And my h of 0 would have gone to the last one because it is shifted 15 times. And my h of 1 will follow here. It will be somewhere here. And what will be here, come here? This h of 15 would have circulated and come here. So here it will be h of 15. Next will be h of 14. So now if you see, they both coincide, right? So or else call this k equal to 15. So only k equal to 15 is the right answer. So from this you can see that for any n-point DFT, right, to coincide with the linear convolution, the k should be equal to n minus 1, which is 15 in this case. Okay. So whenever you solve a question, you need to try to interpret the results also, so that it is useful for you in the future. Okay, when you are solving some similar questions, it will be useful for you. Okay, moving on to the third question. The 4-point DFT of a discrete time sequence 1023 is. So this is very simple. So they're asking for a 4-point DFT. So if you see my x of k, which is the DFT, will be nothing but n equal to 0 to 3 x of n e power minus j 2 pi by 4 into kn. So I can write it out as a matrix. So 4 cross 4 matrix. So 1, 2, 3, 4. Because in this region my k is 0. And in these regions my n is going to be 0. So they are going to be equal to 1. So this is, how do I write? So k and n. So this is k equal to 0. And here my x of n will sit. So my x of n is 1, 0, 2, 3. So my sum of n will be actually in this direction. So I'll write, this is n equal to 1, n equal to 0, 1, n equal to 2, n equal to 3. This is k equal to 0, k equal to 1, k equal to 2, k equal to 3. Because on the left hand side I have my x of 0, x of 1, x of 2, x of 3. Okay. So k equal to 1, n equal to 1, what I will have? I'll have e power minus j pi by 2. And here e power minus j pi, e power minus j 3 pi by 2. And for k equal to 2, e power minus j pi, e power minus j 2 pi, e power minus j 3 pi. Again, for k equal to 3, what will I have? E power minus j 3 pi by 2, e power minus j 3 pi, e power minus j 9 pi by 2. So you may wonder how I am writing fast. Because I have k equal to 1 here, I just multiply it with 2 to get this. And again I take this and multiply with 3 to get this. Okay. So now if you have to simplify this. So 1, 1, 1, 1, 1. E power minus j pi by 2 is minus j. Minus pi is minus 1. Minus j 3 pi by 2. So if you are difficult to interpret this results, you just go to a quadrant. So this is my imaginary axis. This is my real axis. And this will be my angle theta. So minus j pi by 2, where it will be? It will be here. And what is this? This one. This is gonna be minus j. This is j. This is 1 and minus 1. So this is minus j. Minus pi is, you track this itself and you coincide with here. So minus pi is minus 1. So minus 3 pi by 2. So it is somewhere here, which is nothing but j. So this will be j. Similarly, you have 1 minus j pi. We saw it is gonna be minus 1. Minus j 2 pi is nothing but origin itself. The starting real axis itself. So it will be 1. And minus 3 pi, I will again go to minus 1. And 1 minus j 3 pi by 2. So it is going to be here. It will be j. And minus 3 pi is minus 1. And minus 9 pi by 2. So we went here. Again 1, 2, 3 went here. Again 1, 2, 3. It will be here, which is minus j. This you can also write it as e power minus 4 pi plus pi by 2. J pi by 2. So this is nothing but j pi by 2 itself. So which is nothing but your minus j. So this into 1, 0, 2, 3. So now if you write, you will get 1 plus 2 plus 3, 1 minus 2 plus 3j, 1 plus 2 minus 3, and 1 minus 2 minus 3j. This is nothing but 6 minus 1 plus 3j, 0 minus 1 minus 3j. So this is your answer. So let us check. I think I have already ticked. Sorry. So my answer is 6 minus 1 plus 3j, 0 and minus 1 minus 3j. Okay. So let us move on to the next question. So x of n is a real valued periodic sequence with a period n. X of n and x of k form n-point DFT pairs. The DFT of y of k of the sequence y of n equal to summation r equal to 0 to n minus 1 x of r x of n plus r. So we need to find the DFT of this. So if you notice, this is nothing but similar to your x of n convolved with x of, we can call it circular convolution also because it is anyway periodic, convolved with x of minus n. Because in the normal convolution, it will be x of n minus r, but it is here x of n plus r, meaning you are convolving it with minus n. So my y of k will be nothing but x of k, and what is the convolution of x of minus n? For a real valued x of n, it is going to be equal to x star of k. So this is going to be equal to mod of x of k whole square. Okay, so which is option A. But let's say you don't remember all this, right? Or you don't know how to convert this into this itself. Then what do you do? Then you directly take your DFT. So summation n equal to 0 to n minus 1 y of n e power minus j 2 pi by n into kn. And you substitute your y of n equal to 0 to n minus 1. Here y of n is summation r equal to 0 to n minus 1 x of r x of n plus r e power minus j 2 pi by n kn. Now what do? You just reverse the summations like we always do. 0 to n minus 1 summation, again x of r I can take out, summation n equal to 0 to n minus 1 x of n plus r e power minus j 2 pi by n into kn. So now you go back to your x of k. Your x of k is your k equal to 0 to, n equal to 0 to n minus 1 x of n e power minus j 2 pi by n into kn. Now you have n plus r. So you replace n with n plus r. So then what you will have? Summation k equal to, since this is a periodic x of n with period n, I can again go from 0 to n minus 1 here. This is not going to change. Even if it is going from r to n minus 1 plus r, again the total summation will include all the n terms. So this doesn't really matter for me. So I will have n plus r e power minus j 2 pi by n k into n plus r. But I want to get it in this form. So I have to remove this r out. So I'll have e power minus j 2 pi by n k r summation n equal to 0 to n minus 1 x of n plus r e power minus j 2 pi by n into kn. Again, I have removed this r outside only because it is not affected by the summation. It is like a constant multiplier in the summation. So I have taken out. Now I want this term. So I take this to the right hand side. So e power j 2 pi by n into kr is equal to summation n equal to 0 to n minus 1 x of n plus r e power minus j 2 pi by n into kn. So now I take this equation and take this equation. Again here I forgot x of k. And then what I have on the left hand side, I have y of k equal to summation r equal to 0 to n minus 1 x of r e power j 2 pi by n kr into x of k. So again this x of k is not affected by the summation. So I can take it outside. So x of k summation r equal to 0 to n minus 1 x of r e power j 2 pi by n into kr. So now again I take this x of k equation. I'll write it in terms of r because here I have a summation of r minus j 2 pi by n into kr. But here I have plus, so what I have to do? I can take a minus here, but I don't want to do it like that right now. So what I have to do? I will take x conjugate of k and use the fact that my x of n is real. So I'll write x conjugate of r e power j 2 pi by n into kr. So you need to use the fact that your x of n is real valued. So then this will become r equal to 0 to n minus 1 x of r e power j 2 pi by n into kr. So this is what you want. So your y of k will become this one, right? X of k into x conjugate of k. And this is nothing but your modulus x of k whole square. So this is your answer, which is nothing but option A. So in GATE exam, if you know these small tricks, it will take just a few seconds. But in turn, you will be spending some 2 minutes on this. If you're quick enough, you can solve it in under 2 minutes. And which again will not affect your GATE time itself overall. So it is not always necessary for you to know all the formulas by heart them. If you just know the correct equations, whichever you have to remember, and even in this case, sometimes they give the DFT formula itself. So then you only need to know how to quickly solve and get to the answer. And that fast will come, and the quick method to solve will come only through lots of practice. Basically to get the flow going on, right? So you need to practice lot of things, lots of questions. So this will be the last video in this lecture series. And I hope you guys really enjoyed the way we solved question and the way the class was taught. And if you have made it to this far, it's really great. I really appreciate you. Just keep up the enthusiasm going forward. And all the very best for your other subjects and for GATE. So take care, guys. I'm wishing you all a very good. Thank you. Bye-bye.